wanted, I know. Yes, so I wanted to start off this lecture by addressing what I had commented on previously but didn't get a chance to talk about because Professor Mariam Ghaziassetti was giving her expert lecture. So I mentioned that your exam was counted out of 18. You obviously already got an email about that. And so I wanted to just clarify that one of the questions on fracture toughness, right, your fracture toughness, you can't be beyond your fracture toughness because then your material will fracture. That was sort of the point, but I realized that it was poorly worded. So I didn't think that you all needed to be penalized based on, you know, the diction that was in my head that didn't get translated. So that's one. And then the other question was there was a tie-in to thermal expansion, which we did touch upon in way back at the beginning of this course, but tying into elongation was not a direct point that I made, and so that question was taken out. Now, so your scores were adjusted out of 18 for that reason. That was it. And your head TA also caught, with your help, 2 clerical errors about marking Scantron. So those of you that took version A and B would have already received notification saying that we corrected your score because the Scantron key was bubbled in incorrectly. Our answer sheet was correct, but then when it got bubbled in, it was incorrectly marked. So thank you to the 2 of you who pointed that out. We rectified the situation, and so you should have gotten an email about that. Okay, and this only pertains to A and B versions. There's no issue with the bubbling in the Scantron key for version C. Questions? Yeah?
So I got the email from Natalie, but I haven't received an update from, like, score-wise.
Oh, yes. So instead of spamming you some more, that was our way of just saying, we definitely upgraded your score, and she's uploading it to Carmen at some point. So eventually, you should be able to check it there and confirm that, you know, what you got in an email, it should be bumped by 1 point, and then that should translate to the appropriate percentage. Yeah, but that way you know, because we are humans, although, you know, professors are not. We are obviously superhumans, but every once in a while, you know, these earthling ways get to us. Yeah. What was the exam average? Oh, that was... Yeah, so I did have an average. I didn't email it out because I had not recomputed it. I didn't have time to recompute it. I can share that with you over Carmen once I go back and just rescale everything to 18. I believe it was, off the top of my head, the raw score was 75% with a mode that was a little bit higher than that. But once I rescaled, I can, you know, let you know. But that's about the rough ballpark. So you guys actually did better this time around than exam 1 as a whole. So, I honestly don't read too much into one particular average, to be honest, because the material content is different, and because the way the class makeup is I try not to read into it too much because the second exam does cover a lot of mechanical properties, which the majority of you have seen the concept once or twice, if not many times before. So based on your backgrounds too, some of you will maybe do better just based on the fact that you've seen these stress strain curves more so than some of your other colleagues who might not be mechanical majors. So I don't read too much into one singular number, but I do try to look at trends through the years based on other professors' numbers. Now, granted, in the past I haven't taught this class, I've taught this class once, so my own data sampling is quite small, but aggregated from other professors, the trend is that your semester is doing much better than previous semesters. That is a factual statement, no connotation, don't read into it, it just is, okay? I'm not saying anything, it just, that is the facts. Okay. Okay. Any other questions before I move on to reviewing chapter 10? Yeah.
I just wanted to confirm something. The third midterm, it's not going
Right, yep. As I've said before, it is not cumulative. However, all your, you know, right, all the knowledge is aggregated, and so
There's some knowledge that like
exactly, exactly. And I think it does help if you understand concepts from.
comprehensive course wide exam.
Correct. I'm not going to ask you to derive anything from exam 1, but if you know certain trends from materials properties, from, let's say, content that was covered before exam 1, I think it does help, especially when it comes to the conceptual questions. Okay? But that's a general comment, honestly, for like any class. So, yeah.
You said there are issues with vision A and B in the exam too. So will you regrade them?
Wait, sorry, repeat the question?
You said that there is issue with vision A and vision B.
Yeah, they've all been regraded. That's what, so did you take A or B? No. Oh, then it doesn't pertain to you. Okay, let's move on then. Those that are relevant have already been communicated with, okay? It's already been dealt with. Okay, so it's been a while since we actually did some top hat questions, so let's get back to it. This question, let me post it out to top hat for you all. Oh, sorry, didn't mean to do that. So let's review our understanding of TTT diagrams. So here is something that you've seen before, right? So it says here an alloy, but really when you look at the phase diagram and the temperature, you kind of know that it's your iron-carbon phase diagram, right? So it's not just any alloy, it's iron-carbon, and it's instantaneously cooled. So that's really important to know, right? Because we've discussed very briefly, and Professor Phillips during his guest lecture said, you know, there are situations where you are continuously cooling. So here it says instantaneously cooled. That means you drop the temperature as fast as you can to 350 C and held for 5 hours. And then you quench it to room temperature. So what microconstituents would you expect in the final product, right? So here it is, and it would help if you actually saw the time. So here's your transformation, temperature 727. So you go down to 350 instantaneously, and then you hold for 5 hours. So clearly you can already see that your x-axis is in seconds, not hours, so please note that. And it's typically in seconds or minutes. That's how it's often referred to, or reported, I should say. And then I guess if you didn't know, and you scrolled all the way down, you would have seen, yes, it is the phase diagram that you all know and love from chapter 9. So what microconstituent would you have? Would you have coarse pearlite, fine pearlite, bainite, martensite, austenite? Oh, I wonder, okay, yeah, that's right, it got transferred correctly. Unfortunately, this figure and the options are not all going to fit, so I'm going to scroll back. So some of you would have seen this already in your recitation if you had it on Tuesday, so it should just be a review for you. You can rule out one answer based on the phase diagram. Or if you came in early enough and saw when I exposed the answer, so. All right, most people have submitted their answers, so I will await the final 5 for another 5 seconds or so. Oh, fabulous, okay. There continues to be more and more of you. All right, we're at 100%, so I think this percentage is going to be high, but let's see. Okay. Well, yes. So an overwhelming majority of you said 80% bainite. So it is exactly what you're thinking, which is if you have 0.77 weight percent carbon, this is your phase diagram. Your composition does not change. This is it. This is the chemistry that you have. Then you drop the temperature very quickly to 350, which is about here. And because it's instantaneous and it's isothermal, then you can assume that you've beat the nose. That means you haven't gone into this territory yet. And so if it's all the way down to 350 and you wait 5 hours, right, that gets you to here-ish. Actually, it gets you to 1, 2, 3, 4, 5. So it gets you to about here. So that means you've gone through 1% transformation, 50% transformation, and now 100% transformation. You're well beyond 100% transformation to bainite. Okay, so that's how you would be able to read it. And we went through very briefly some examples last time when I lectured where you could end up in the middle like this. And so if you're here at the 50% mark, that means you've transformed your material from austenite to 50% bainite. And then if you drop the temperature then you would get 50% martensite once you drop the temperature here, okay? So just to review, if you have something like this, right, okay, sure, because I ended up there. So yeah, you get 50% bainite, and then you drop it, you get martensite. Obviously, these are pretty precipitous drops in temperature. This is not actually physically possible, right? I mean, it is impossible to drop 100 degrees Celsius in less than a second. That's extremely difficult to do unless you have some pretty specialized equipment where you can do that. And if you do have that, then you're a bulk metallic glass person, and this is what you're doing for a living. Otherwise, right, air cooling, it takes a long time. So anyway, so it is bainite. Okay, so let's move on, mainly because I would, so Professor Gaziasetti has talked a lot about strengthening, so I will, move on from that, just to say that, just to reemphasize some points that she made about precipitation. So if you have a phase diagram like this, and you drop the temperature down slowly from this, kappa phase down to this, okay, sorry, let me move out of the way, down to this theta and kappa phase, right, whatever Greek letter you want to use, if you cool it down slowly enough, right, you allow the growth of the second phase precipitate to form. And that typically forms at the grain boundaries, as we've discussed, because kappa is a solid phase, right? You're not going from molten anymore if you're starting at this kappa phase right here. You're starting from a solid phase, and you're transforming from solid kappa now to solid kappa and theta. Okay, so that's the scenario that Professor Gaziasetti was talking about. Now, there are a lot of heat treatments that you could do to increase ductility in your material or increase the strength a little bit. So we talked about what happens when you quench very quickly austenite down to room temperature. If you can beat that nose, you're going to get martensite. Okay, that's great for you, and the strength will increase, but you lose a lot of ductility. Your material will be much more brittle than what you want in our iron-carbon phase system. And so what people typically do is they'll drop it down to martensite, and then they gently heat it up again. It's called tempering. So that you heat it up again, and then you age it so that you can get these fine precipitates that are not actually at the grain boundary anymore. Okay, so these fine dispersions will get you a little bit of your ductility back, and also just some strength as well. So it's always a push and pull in terms of, okay, well, what strength are you optimizing for? And so one of the questions that came from the front is like, okay, I have this intrinsic strength in the material, what can I do with it? You can do a lot with it, and the next chapter, chapter 11, that we'll start today, is just what can you not do with it? And so there are a lot of companies that have made their money in just knowing how to heat treat a material. And a lot of those companies are in Ohio. There's a huge history, in Pennsylvania and Michigan and Indiana. There's a huge history of forging and metalworking and all that. And so there's a lot of knowledge that already exists, but they're not always so open, because if you're a company and your bread and butter is that you know how to heat treat a material to get a desired property so that you can sell it to a customer, it is not in your best interest to share this secret. So then you don't go into academia, because I'm all about sharing information. But that's fine, you know, everybody has their objectives in life, and that's fine. So there's a whole lot of money to be made in just understanding how to heat treat. And a lot of times these companies are not going to file patents, so you're not going to find it in the patent literature. It's just going to be a trade secret. They're going to keep it in-house, and the only way you learn it is, of course, you join the company and sign a non-disclosure form. So that's how that is, okay? Okay. Oh, there's like fancy animations that, you know, Shackelford provided. But anyway, yeah, you drop, you bring it back up. Okay. Let's, okay, so this was the summary slide that, you know, that she brought up, and so I really don't need to belabor the point that if you're wanting to increase the strength of a material, you're going to want to impede dislocation motion. And so Professor Gaziasetti re-emphasized some of the points that we've already discussed in chapter 6 in terms of, you know, grain size refinement. So just make your grain smaller, you know, so you have more grain boundaries. And grain boundaries stop dislocation movement, because it's really difficult for this dislocation to keep on climbing, because the energetics there is just too high for it to overcome. Solid solution strengthening, she's also talked about that, and we talked about it in chapter 6. Strain hardening, right, working a material. And then precipitation strengthening. So that really rounds out transformation, phase transformation and heat treatment. And all of these tricks that one can do, you know, in terms of recovery, recrystallization, grain growth, is just all to manipulate the microstructure so that you get your desired balance of strength versus ductility. Okay. And, you know, as you've seen, the chemistries change quite a bit. When we're going from 0.7 weight percent carbon, right, 0.77, and then you go 0.78, you're in the eutectic land, right? And so changing and altering these chemistries, even subtly, have significant implications when it comes to the end result. And the end result, of course, has societal impact, right? Professor Mike Mills has talked about engine blades, and, you know, he glazed over the fact that the blades that were in the engines of the Southwest airplanes that failed were from GE. GE is, of course, right around the corner from us in Cincinnati, and so we obviously like to support our local, well, okay, GE is not just local, but local economy and global economy. But, you know, we really do have to learn from all of these mistakes. Granted, the last airplane that, that failed, I believe, was actually a software issue, not so much a material-specific issue. So, so that's that. But certainly, what you do in the lab does translate into, you know, the end result. So, speaking of end results, we're going to skip right to chapter 11, where we're going to start talking about structural materials. You can think about structural materials as both the type of materials that, you know, come probably intuitively to mind, which is, of course, metals and metal-based alloys. You can also think about structural materials in terms of ceramics. And maybe that's not so intuitive because of some of the mechanical properties that we've talked about, right? That ceramics can have higher strength, but they are brittle, right? And so there are certain applications where you don't want this in your life. But I did pull up an example of a glass that that Corning has made, and of course you're all the beneficiaries of the last 20 years of scientific research from Corning. Any guesses, or whoever came in early enough to see me Google this? I know some of you were here. You saw me type it in. You can just shout it. Okay, wow. Very sheepish today, I have to say. Yeah, structural materials. So let's see. This is Mythbusters. We don't really need to, yes, the 3-point test. You've all seen this. Okay, so this is what you expect out of a glass if you're going to use it structurally, right? It's going to have this fantastic fracture beyond its fracture point, right? Fracture toughness. And then he holds up this other glass. And notice that they're wearing goggles, safety first. Right, and so he's going to try to do the same experiment, but what do you see? You see it bend. Okay, I don't know what this is, so I'm going to maximize that. Right, so you can see their discussion of this glass being flexible, and that's not at all intuitive, right? And then what they can also do is laminate this glass onto stainless steel, and then do what with it? And then put it in 5 billion phones in the world and sell it to you. This is the result of why when you drop your phone, I will not have a demo on this because I like my phone, but when you drop your phone, the fact that, oh, I'm sorry, forgot about the lights. Right, so he's inspecting glass on stainless steel, and they're obviously very intrigued about it, and so they're going to do an impact test. So, they're going to investigate the hardness, although this is not how one typically does a hardness test, but this will suffice for TV. So stainless steel ball bearing, they're going to drop it. Glass, of course, is not going to fracture, as you anticipate. It's going to make a dent. So you see a little bit of a dent here, but it doesn't fracture the same way, right? And what you'll learn from chapter 11 is exactly why it doesn't fracture. It's all because of a subtle chemistry change. So the glass that you see that are cheaply made in everyday life has what ion in it other than silicon and oxygen? For the ceramists in the audience. Ethan is shaking his head. He is not a ceramist. You were going to say silicon. Yeah, well, so glass is silicon dioxide, basically, and depending on the crystal structure, right, it can be ordered or it can be amorphous. Yes. It's an alkaline. So start going down the list. All right. It's sodium. It's also a good guess. Anytime anybody asks you to guess something, it's going to be silicon or sodium, given the abundance of material elements in this earth. So anyway, that's one way that glass and ceramic materials have just absolutely transformed the way we live. Without this, your phones, well, maybe it would be better for Apple because then your phones would just be cracking left and right. And then they would just sell more phones. So it's hard to say what is economically better for them. The other way that you can really think about structural materials and how you can manipulate the mechanical properties to, basically transform how we live is through, it's through this. So what is this? He's pointing light out of a flexible wire. What seems like, oh, okay, I don't know what's happening. Yeah, so he's twisting this. There's a light coming out. This is all glass, by the way. Well, okay, not all glass. The material outside is not glass. It's a plastic. So he's bending glass, which is not something that you would expect. What is that? What is he bending? all the ECE folks in the audience. Fiberglass. Yeah. I mean, glass has basically transformed. I mean, the only reason that Apple even has something to operate on, right? That everybody taps into the fiber optic network, right? The fact that you can talk to somebody in anywhere in the world is because of all these fiber optic cables, and it would absolutely not be possible if it weren't for the fact that Corning, in the middle of upstate New York, decided that they were going to be able to do this. So not only do they do bakeware, which is great, right? You can bake your brownies, you can bake your cakes, but now you can talk to everybody else in the world because they enabled the internet, as we speak, through glass engineering. So it seems like, haven't we figured out how to boil, not boil, but how to melt down sand to make, silicon dioxide glass? No, apparently not. And this is obviously quite recent. And so there's a lot of engineering in glass. And of course, you have Owens Corning right around the corner in Granville. It's about 45 minutes from here if you're not familiar, although I surmise most of you are familiar. So anyway, that's my motivation for this chapter is, even materials that aren't seemingly structural in a way can be structural materials, because if these glass fibers, the fact that the majority of this cable is your glass, that makes it structural. It's not just a component anymore. It is a structural component, right? Its mechanical properties matter in terms of how you work the material. So that's what we'll talk about today, right? This is the classic, as I said in the first lecture and the second lecture ever of this class, is that understanding structure is one thing, but then processing it, knowing the heat treatment, knowing the phase diagram, I mean, that absolutely is the rest of engineering, because it all ties back to the properties and the performance, right, of your material. And so we basically are on this loop of, we want some endpoint application, we want to know how to process it, and then we need to understand, well, what happens when we do process something, what are the structure, property, performance relations of this material. And so that's a huge buzzword that you hear these days is, what is the structure, property, performance of a material. And so your chapter 11 goes through an excruciating detail into how we talk about materials and how we classify materials. So I think it's come up before where you've seen, in your homework and your exam, people refer to all these materials and all these alloys as, okay, we're dealing with 1040 steel, so that's iron with 0.4 weight % carbon. So all this jargon, all this nomenclature comes out of the taxonomy, right? It comes out of this systematic classification of materials, the same way we can classify animals on Earth with their families and the kingdom and all of that. We have the same way of talking about materials and doing it in a systematic way. So, certainly we've already talked about the different classes of materials, the ceramics, the hybrids, the metal alloys, the polymers, right? And we'll talk much more about polymers come chapter 12. And we have quite a number of guest lecturers who think a lot about polymers and how to make it mimic certain bio functions. And it is extremely cool, I think, even though I don't do bio research. Right. And so anyway, so back to my point about classification, lots to do. And so when you see something like aluminum 6061, if you work in the aluminum alloy industry, I think you know off the bat, what 6061 means. If you're like me and you're not a metallurgist, then you just go look it up, okay? And that's fine. But there's a rhyme and reason for all of these numbers. So your book goes through, your table 11.1 goes through all of these great details, right? You have your carbon steels, 10XX, so that's, you could be 1040, it could be 1070, it could be 10 whatever. If you heat treat it and have sulfurization, then it's 11XX, and I mean, really, the list goes on and on. So these tables are really just good, I think, for reference, not for memorization. Unless you happen to work in a lab that deals with one material, then I think you start to know that class of material, that naming system very well. But I would say the takeaway for chapter 11 is that it's a very good reference. Same thing for stainless steels, right? So you could see that for these knives that are attached to some magnetic component on the wall, they have to have some magnetic iron in them. Otherwise, they wouldn't hold up the same way they would, right? And so if you remember your demo where, Paul, your TA, had the iron piano wire, resistively heated, and at a certain point, the magnet dropped, right? It passed the Curie temperature. It passed the 710 degrees Celsius point. And then beyond that, beyond 910, it would phase transform from BCC to FCC, right? And so if your stainless steel your knife is magnetic like this, then okay, there's got to be some BCC iron in there, right? If you know it's a steel. So, I mean, all these things, you can sort of tell. Then, of course, you can go down the line and know, okay, well, if I want some corrosion resistance, I need to add in some chromium. That changes the numbering scheme from 304 austenitic stainless steel to 316. That's a very good grade. If you ever buy stainless steel, buy the 316. It's very resistant to corrosion and has some chromium in it. Because of the chromium, it can also form a chromia, chromium 203 passivating layer, the same way alumina forms a passivating layer, the same way SiO2 forms a passivating layer on silicon. So if you're ECE, you're very familiar with this. If you're more corrosion, MSE, welding, others, then you would be more familiar with the other oxides that form, right? So that's fabulous and all. And then you could think about, okay, well, we've talked a lot about low carbon content. What happens when you have a lot of carbon content? And I believe someone had asked about graphite or just a lot of 100%. What happens when you go beyond 6.7 weight percent carbon, right? You get all this graphite flakes that come out. Not the worst thing in the world, because you do restore some mechanical properties, but then you have graphite everywhere, and so you might pay a price in terms of strength there. I should also note the cast iron. So in your book, they mention cast iron as being basically between 1 to 2 weight percent of carbon. So when you get to such high carbon content, right, you do run the fact that it's going to be more brittle. So if you drop your cast iron pan, there is a possibility that it's just going to fracture on you based on its brittleness, and it's not going to behave like an iron, a low carbon iron pan. Okay. Something I should also mention. So even when you have a low carbon content, so what we were talking about before was 0.77. Here it's 0.68 weight percent. But whatever the eutectic composition is, when you drop that temperature below the eutectoid temperature, and then you wait long enough, we said, okay, it's going to form perlite, right? We talked about the microstructure. We talked about the phase diagram. We can compute all the phase weight fractions that we want. But then if you age it long enough, you get all the stripes, the microstructure, that's the layered microstructure. If you wait long enough and allow diffusion to happen, you actually will get some spheroidal microstructures that look like this. So not great, but so there is actually a penalty to pay if you age it too long. So certainly processing plays a role in terms of enhancing mechanical properties in these systems. So, something that I also want to mention is that it's really energetically consuming in terms of getting ore out of the ground and then getting it to whatever metal that you need to get it to. So if you're digging up iron oxide out of the ground or calcium oxide, all of that, there's a lot of CO2 that gets formed. And so I alluded to this earlier in lecture 2 of this course, where I said, you know, a lot of the ways that we've been mining and purifying metals from ore it's just basically killing this earth. I mean, it is a total death to climate change, or the climate, I should say, because there is so much CO2 that gets generated, and then once you dig it out of the ground through purification, you generate more CO2. So there's a lot that we can do. I mean, we know a lot about manipulating materials and processing them and all that, but the step before that, there's a huge need in terms of environmental science that we need to do to maybe not go this route in terms of reducing the oxide that's in the ground into a metallic ingot that you could use. Okay, so that's my 2 cents on climate change. So wrought metal products, so that means they're worked, right? So when you work them, there's a lot of ways that you can actually, make the thin sheets of fill in the blank. Certainly, roll milling is quite important. So whenever you get aluminum slabs or what have you, it's all because of this, right? They just roll it out. They have the huge ingots, and then they roll it out into sheets. So your aluminum sheets, came from somewhere. It's sort of like your baby carrot came from like a larger carrot. Yeah, there's a lot of waste, okay? So there's that. So there's a lot of details on forming, casting, joining. How do you manipulate all of these structural materials, in terms of getting the shape that you want? There's a huge industry in this state, and there are experts that can tell you about just one system, but you should know that there's just a lot. So there's forging, rolling, you can draw and extrude to get all of these shapes. And of course, we're talking about metal. So when we talk about ceramics, you can't really apply the same methodology that you do, right? You can't roll in the same way for metal, for ceramics as you do for metals. So, right, hot working, cold working, there are obviously pros and cons for either, right? So for hot working, you can manipulate the microstructure and recrystallize. You can use less force to form the material, but of course you have to get the system up to temperature and then work the system. So clearly you want to cold work if you're going to want to avoid the huge energy costs that you have to pay up front. So that's something to think about. Certainly, so that was that was forming. Certainly you can cast shapes as well. So if you have a really complex system like this, right, like an automotive engine block, you're certainly not going to roll it out and get this morphology, right? You're going to have to cast. So casting is exactly what you think it is. You take it into the molten state and you dump it into some mold, right? After that, though, to get all of these finer details, all these rivets and things like that, I mean, there are processing procedures that go on after this. But if you wanted something that was quite complex and big like this, casting is the way to go for that. And of course, you could see all of these shapes are, they got different dimensions and all of that. So casting is one way to go. Aluminum alloys, all I have to say about that is that there's another naming system. I don't really expect you to memorize any of this, by the way. Chapter 11, as I said, is just a really good reference. So there's a lot that's packed in there, but your takeaway from chapter 11 is just understanding the different ways of processing metals versus or structural materials for, let's say, metals versus glass. Okay. So we've seen this plot before in one of your homeworks in chapter 6, but we'll revisit again because I want to emphasize that once you cold work a material, it does change the tensile strength and it does change the percent elongation or ductility, right? So when you cold work a material, certainly the dimensions change. So if, let's say, you're rolling or you're pulling, right, your area gets smaller, right? So the percent cold work is basically that difference, but in percentage form. So, oh, interesting. Okay, well, my animation has changed, but certainly when you see the amount of cold work, right, it's just, if you start out with some area, that's your A naught, you know, you're going to have some new area that's a little bit smaller because you worked, and then you divide that by, you know, your original, and percent cold work is just 100% of that. And your area, of course, is just pi r squared. So you have a tube, let's say, of material, your area is just pi r squared of that, where r is the radius of your starting material. And then if you cold work it or you make it smaller, you extrude it, the area is going to be smaller. So your A sub f is going to be smaller. So you can say, okay, well, how much did I cold work it? Well, if you cold work it at, let's say, 10%, then you could see, okay, so you read it here for an 85% copper, 15% zinc. Okay, so it started at 350 MPa. If you cold work it a little bit more, you can increase the strength to a little bit over 400, and you can, you know, see the point there. And then, of course, the payoff does actually start to plateau after a while. Okay, so you may or may not see this in your homework for homework 6, by the way. So that's how you read these types of plots, is how much did I cold work, what is the dimensional change, and how does that affect my strength or ductility, percent elongation, and hardness as well. And hardness, as you recall, is the resistance to indentation. Okay. Okay. Ceramics, so many. Yes. Yeah. Yes, yes. So I'm talking about, like, if you have like a typical dimension like this, your area is based on that. Yeah, thanks. Okay, so many things to talk about when it comes to glasses, clays, and all that. So beyond pottery, which, by the way, is a fabulous hobby if you ever need a hobby. Lots to do with that. And so certainly we've come a long way from just making pots to hold whatever, grains and presumably some fermented alcohol back then, because that's how you store beverages without killing yourself of bacteria infection. Certainly we've come a long way to understanding ceramics and glasses, right? And so, you know, when we're talking about the different types of ceramics, we, you know, can call them glasses, clay, refractories, abrasives, cements, advanced ceramics, all of that. So let's break that down as to what are the challenges in terms of dealing with ceramics. As we mentioned, they have high strength, but they're brittle, right? Their high melting temperature also is not a great thing when it comes to actually processing the material, because materials that can withstand high temperatures before they melt means that if you want to do something with them, you have to get to that high temperature. And the ceramics that we're talking about, you know, the zirconias and the carbides, their melting temperatures are at, you know, 1800 degrees Celsius, you know, 2000, 2200 for some of the carbides. That's extremely challenging to build a furnace out of, to even do your processing. So, you know, one, what material is going to withstand that temperature, and then how do you get that material into that furnace form so that you can use it to manipulate another ceramic. So these are really challenging, and as you should know, glass, right, melts at about, starts to get molten and loses structural integrity at about 1200 degrees Celsius. So anything higher, so you can't even use glass as a crucible, right? You have to then move over to a zirconia and other crucibles to even hold your material. So there are a lot of challenges. So if you're looking for a box furnace and you just need to heat up to some mild temperature below the glass melting temperature, you're looking at maybe $1,000. As soon as you go over that threshold and you ask a vendor for a high temperature furnace, I mean, we're talking tens and, very expensive. And I'm talking about, materials that, a furnace that's like this big, that holds like one little thing that's lab scale, okay? So if you're a large company and you're having to deal with ceramics, this is the challenge that, that you're faced with. But obviously, with fiber optics and all the glass science in the world, clearly, we've come a long way in terms of understanding how to form glass, and then we'll also talk about particulate forming and cementation. And so here we come back to our initial discussion of what is in common glass, like everyday glass is soda glass. That is the cheap glass that you can buy. They have sodium ions in there. And so you could think about the viscosity of silica. So if you have regular silica where it's just SiO2, it could form in a structure like this, but you can bring down the viscosity and by doping in sodium ions, and then you bring the viscosity down so you can work with the material this way. And so you could see the viscosity here at annealing temperature. You can bring it down to, say, 600 as opposed to what I was telling you about before, which is like 1,300 degrees Celsius. So it's actually quite advantageous by just doping in sodium ions. The Gorilla Glass that you saw in the YouTube video at the beginning of this class, today's lecture, is completely different, because if you have just soda glass where you have sodium ions in this SiO2 structure, it fractures like you see. So what Corning was able to do was they took out the sodium ions, they exchanged it with potassium ions. So potassium is just larger, and it absolutely, so you went lower in the periodic table, and it absolutely changed the mechanical properties of glass, right? And so before, no one would ever think to coat stainless steel and much less make a phone out of glass. But now, certainly when you drop your phone, you expect it not to fracture. Now, some of you, though, have cracked screens, I anticipate. That is slightly different, right? Because your touch screen is indium tin oxide, and so there it resistively measures your touch to the screen. That's a whole different beast. But anyway, so yeah, Corning, 20 years ago decided, yeah, we're going to change it from sodium to potassium, and it's revolutionized the phone industry. Okay, and I say that sort of facetiously, like, oh, one day they decided to switch out the ions. It takes many years, okay? It takes a very long time and many researchers to sit down and think about experiments where, excuse me, where you can think about, where you can do research and to change and enhance mechanical properties. And in fact, one of the co-inventors is Professor John Morrow, M-A-U-R-O, who's now at Penn State. He was at Corning for 18 years, or maybe 16 years. But anyway, he's coming to the Material Science Department this Friday. The Materials Department has our weekly colloquium, our weekly seminar at 3 to 4 p.m. Every week. And this week, we're hosting John Morrow, one of the co-inventors. So if you ever wanted to ask John, why or how or what led you to this discovery, you can actually talk with him in person. Yeah, so his lecture is 3 to 4 p.m. and then he usually will stay for a few minutes to talk with people. And so there's your chance if you're free 3 to 4 p.m. Okay. Right. The last thing I want to talk about in terms of strengthening glass is if you've ever heard of Prince Rupert drop, where basically you melt glass into these little droplets, these little tear-shaped droplets. You drop them down, and because there's a compressive stress outside and tension on the inside, it actually is quite strong, but you have a lot of energy in there. And so what you've seen with some of the examples is that people will just break the little tail and the thing completely shatters, but if you touch the little drop, not where the tail is, it's completely fine and it's quite strong. that is glass engineering in a nutshell, right? So what you typically do is you have glass that's hot, and then as you're cooling it, you can spritz the surface and make it cooler. Or with Prince Rupert's drop, you can just drop it into a bucket of water, and the same thing will happen. And so you get compression at the edges here, and then tension on the inside, and that creates stronger glass, but then there will be a certain failure point where when you touch it, it just completely shatters. Okay. Let's see. Firing, I've already talked about that. So, yeah, in terms of processing glass, something that we've also talked about at the beginning of the course as a whole is sintering. Right, we looked at single crystalline ceramics where they're not transparent when it's sort of polycrystalline, but then when you make it single crystal and sinter and basically just press it, you can get optical transparency, right? And so certainly, even though materials that were normally not that don't possess optical properties that you might want, which is, if you want transparent ceramics, you can just press it and sinter the material, and it will remove all the pores and make the material transparent. So I believe this is where I want to leave off. For Friday's lecture, we will talk more about structural material and structural material engineering. Professor Glenn Dane is coming, and he is fabulous, and he will talk about lightweighting of material and how do you manipulate structural materials and make them lighter but stronger. Okay, so anyway, I'll see you Friday. Hi.
Quick question. So
Yes.
We've been focusing a lot on like metals and stuff this semester. Are we gonna hit up more on like ceramics and stuff later on, and polymers, or is it just mostly the focus?
Polymers. Yeah. So chapter 12 is polymers and composites.